All right, so this video is going to look at graphs of proportional relationships. So yesterday in class we looked at some graphs and tables for some robotic balloon popping dogs, and we figured out that the only dog that had a proportional relationship between time and number of balloons popped was the dog who started with 0 balloons at 0 seconds and continued popping at a consistent rate. And so from that we can know that graphs of proportional relationships are always straight lines, and they always go through the origin. And in the case of many situations, they start at the origin because it doesn't make sense to have negative time or negative balloons popped. So, graphs of proportional relationships, straight lines that go through the origin. So without even knowing any numbers, we can tell by looking at a graph whether it's proportional. So this would be an example of a proportional graph. It could be a little less steep. It could be a little more steep, but all of them start at the origin and proceed in a straight line. An example of a non-proportional graph would be one that doesn't go through the origin. Maybe one that's slanting down that way doesn't go through the origin. It could start at the origin but then have a curved trajectory, which is also not a proportional relationship. Beyond just looking at the shape of the graph, however, we can use the information that we see in the graph when we have values on our axes to do a few things. We can interpret points, we can determine proportionality, we can find the constant of proportionality, and then therefore also find the unit rate, and specifically look at where the unit rate falls on the graph. So the first thing we want to do is look at interpreting some points. And this basically just means understanding how the graph is put together. So here we've got gallons of water someone has available and how many minutes of a shower they're able to take with that many gallons. So the minutes you're allowed to shower depend on how many gallons of water you have to use. And so we can see here we've got a scale going up by 1s on the minutes. We've got a scale going by 20s on the gallons. Always need to remember to look at our scale. And in fact, that's a note that I'm going to put up here, because one common mistake I see often is the assumption that these are always going by 1, and that's not always necessarily true. So let's say, for example, we have here point A. So point A is at between 20 and 40 on the x-axis. And so this is going to be 25, 30, 35, 40. So that's going to be at 30, 10, 30 on the x value, 10 on the y value. And what that means is that we have 30 gallons, and that's going to give us 10 minutes. So the point 30, 10 means 30 gallons will give us a 10-minute shower. So we could say 30, 10. And 10 minutes. So again, the reminder that this is the x value that we list first, and this is the y value that we list second. Okay, so we could also go a little closer in and say this is 15 gallons, and at that point we could take a 5-minute shower. We can also answer questions like, in 15 minutes, how many gallons of water would I use? So we'd go here to 15 minutes, come across, and each of those lines is 5, so that's about 45 gallons in a 15-minute shower. Now we're also able to determine proportionality. Okay, so knowing that this is a straight line that goes through the origin, we can tell it's proportional. We can also pull some of that information off and put it in a table, and that can do one of two things. It can help us just double check that it's proportional, and that can also help us with our next step, which is going to be finding the constant of proportionality. So this is going to be gallons, x value, and this is going to be minutes, so y value. So let's take the points that are nice here that have been already notated, so we know they're on whole numbers. So we've got 15 gallons is a 5-minute shower. We've got 30 gallons is a 10-minute shower. We've got 45 gallons is a 15-minute shower. 60 gallons, 20-minute shower. So, looking for that constant of proportionality, which will lead us down to our next step down here, is we do y divided by x. So that would be 5 divided by 15, 10 divided by 30, 15 divided by 45, and 20 divided by 60. And if I simplify all of these fractions, I see they all simplify to 1/3. So that confirms that visually the graph looks like it's in a straight line, and it actually is, because every time the output divided by the input is 1/3. So that also means down here that we know that our constant of proportionality is 1/3 based on our simplification of our y divided by x over here. So what information does this give us? Well, if the constant of proportionality is 1/3, that means we're also always multiplying gallons by 1/3 to get to the minute. So that means we could say that gallons times 1/3 gives us minutes, or minutes are 1/3 of the gallons. So let's take that to the unit rate. Now, we said that the unit rate is the same as the constant of proportionality, and it's also the place on the table where the input is 1. So if we have our table here and we have our gallons, we have our minutes, we're working with things like 15 and 5, okay? And we know that we want the input here to be 1. So we know that the constant of proportionality is 1/3. So we know that we need to multiply the input times 1/3 to get to the output. Again, this makes sense because if we're multiplying everything by 1/3, then 1 times 1/3 is 1/3. This is the constant of proportionality. It's also the unit rate, which means the output when the input is 1. And so what this means is for every 1 gallon, you can take 20 seconds of a shower, which is 1/3 of a minute. So for every 1 gallon, you're taking up 1/3 of a minute of a shower. So this number, the constant of proportionality and the unit rate, also shows up on the graph. So we said that this number, the unit rate, is when the input is 1, which means on the graph, that's going to be when the input value, the x value, is 1. So if I go here, okay, this is 5. So actually on this graph, I'm going to have a hard time actually pinpointing the location, but I can use what I know about the unit rate and the constant of proportionality to tell where that point's going to be. So here's my 5 gallons, but I'm concerned about here where 1 gallon is. Well, we know from here that when the input is 1, the output is 1/3 based on our table and what we know about the unit rate. So we know that that point is going to be here where their number of minutes is 1/3 of a minute. So we know, even without being able to see it on the graph specifically, that that location is going to be input 1, or x value 1, output value 1/3. This number, the constant of proportionality, and the unit rate is the output when the input is 1. So always we can describe this point as 1k, and k is what we're using there to represent the constant of proportionality. And what's cool about that is every time you have a graph of a proportional relationship, you know that when the input is 1, the output is going to be k, the constant of proportionality, which is the same as the unit rate, and it's going to tell us for every 1, in this case gallon, how much in this case minutes, we get, so we know for input of 1, we get out 1/3. That's also what we multiply our input by to get to our output for every point on the graph. So you can see that the constant of proportionality and the unit rate and this point on the graph are all connected to each other. All right, let's look at an example of how we can use this idea of proportional relationships in graphs to answer some questions. So here's our situation. We have Tyler, he's at the amusement park, and we know he walked at a steady pace from the ticket booth to the bumper cars. So here's my graph. I've got time in seconds, and I've got distance he's walked away from the ticket booth in meters. I can see I've got the same scale on both axes, so I know that 1 square represents 5 seconds, but also 5 meters. Remember, that's not always the case, but in this case, it is. All right, so we see that the point on the graph, 40:50, shows Tyler's arrival at the bumper cars. So what does this tell us? Well, remember we list X, or input, in this case time, followed by Y, output, in this case meters. So that tells us that it took him 40 seconds to walk 50 meters. So that gives us some basic information about how long it took him to walk those 50 meters, 40 seconds. All right, so now we want to plot at least 3 more points. So we know here that we're counting Tyler's distance from the ticket booth. If he started at the ticket booth, that means he must have started at 0 meters. And obviously he started walking when he'd been counting 0 seconds. So that means he started at 0, 0. And he walked at a steady pace, which means the line showing his progress is going to be straight. That means this is a proportional relationship because it will have started at the origin and gone in a straight line. So using that information, there's a few ways that we can plot a few more points on the grid. First of all, we can add the point 0, 0 for sure because we know that he started there. So we have some options. First of all, we could take the information we have about time versus meters. We know there's 0, 0, and we know that there's 40, 50. So we could take those relationships and make some equivalent rates. So we could divide both 40 and 50 by 10 and get 4 and 5. And then we could multiply or divide those by another common number. Let's say we multiply them both by 5. So we've got 20 seconds is going to take 25 meters. Because remember, as long as we multiply or divide both values by the same thing, we're making an equivalent rate. So we could figure out some points that way and then plot them. Our other option is knowing that this is a proportional relationship. We know that it's going to go in a straight line. And we can connect points on this line because when you're walking continuously. So we could draw a line there to help us as well. So here's the point 2025 that I found here. That's here. Okay. And then I probably here want to use a combination between the table and the line to figure out one more point in between. So I see here 4, 5. That's going to be somewhere around here. So I could kind of estimate that. So there's a few more points. And again, I could continue making points on the table and attach them to the line. The line's an easy way to see the trajectory. Sometimes it's hard to see where the exact points fall, so it's always good to double check with the table that you've got points that are in the correct relationship. And as we've already discussed, the point 0, 0 in this situation means that at 0 seconds, Tyler walked 0 meters. The next question asks us about the constant of proportionality between time and distance. So we already have a table written up here, so we can go ahead and use that table to help us out. Let's go ahead and do y divided by x. So let's see. Here we've got 50 divided by 40 is 1 point. Here we've got 5 divided by 4, that's another point. Here we've got 25 divided by 20, that's another point. And I notice that if I simplify all of those down to their simplest form, I get 5/4. So that means our constant of proportionality must be 5/4. So what does this tell us about Tyler's walk? Well, let's remember that our constant of proportionality is the same as our unit rate. So I've added a line to my table here where the input is 1 and the output is 5/4. That's what the unit rate is, and this is our constant of proportionality. And so that tells us that for every 1 second, Tyler walks 5/4 of a meter. So that ties into question E. How far away from the ticket booth was Tyler after 1 second? So that would be that point here on the graph, which is kind of hard to see, but we could try to label it anyway. That would be 1 second and 5/4 of a meter, because that's our unit rate. Input 1, output 5/4, x1, y 5/4. And our final question asks, if Tyler wanted to get to the bumper cars in half the time, how would the graph representing his walk change? So in whatever context you're watching this video, I want you to try this one on your own and have a conversation with somebody about what you figured out. That could be another classmate or that could be your teacher.